So in the last video, we saw how to use the ONNX runtime in C# to use different models. So outside of the Microsoft official APIs that use the English-centric Roberto model, we can now use different models pre-trained on specific tasks or on different languages. The next challenge is to retrain a model on our custom data and consume that model in C#. Unfortunately, we cannot retrain those exported ONNX models, so we'll have to go back to the framework in which they were originally trained in, which is PyTorch in Python. So I retrained a pre-trained named entity recognition model that performs on the Dutch language. I retrained that on my custom Dutch dataset. To do that, I first had to prepare my dataset, and that did not exactly go as expected. So I would assume I could just label my dataset as I would specify which are non-entities by assigning an O, and which are the entities of interest by assigning a specific custom label like name, age, breed, ref ID, and then basically say what makes up the multi-token entity. So 7 years and 11 months is the entire age. Then I had to label it as follows. But that went horribly wrong because of tokenization. So this naively labeled dataset had to turn into something more looking like the following, in which there are some added non-entities. And I'll show you why in a bit. So there are good tutorials to follow, examples that can get you pretty far. You have to, of course, adapt it to your task and model. So I'm using the Robert Dutch model, pre-trained for named entity recognition with its Tokenizer. And that model I want to retrain on my custom dataset. As we can see, this model was trained to recognize the following entities: the person, organization, location, miscellaneous, and non-entities. What you also notice is there's only B's, Y's, and O's, which is a more simplified way of labeling our entities. And you have to know each dataset can have its own labels, maybe slightly in a different order and so on. So important to get that. Let's just check out an example for named entity recognition, a dataset which doesn't have the problem that we have. Basically, all the words get tokenized. So the sentence gets split into tokens or words in this case, and the labels are there. So it's labeled, and then the index of the labels are the NER tags, named entity recognition tags, which are basically borg has index of 3, 0, 1, 2, 3 in the labels. So that's what that means. Note that it says tokens at the top. And then if you see on Friday and then a special character, it's split on words, on special characters. It could also be split on parts of words and more. That's depending on the tokenizer. This looks like a fairly simple one. It doesn't add any extra symbols like start of sentence and end of sentence or any other symbols. The tokenizer that we were using, a Roberta-based tokenizer, behaves a little differently. And what happened here is a Dutch sentence got split into tokens, where most of the words are a token prefixed with a special character, meaning it's not the first word in the sentence. And it even has the start of sentence token and an end of sentence token, and then padding, which can be turned on or off. When you want to input multiple sentences at once into the model, or to train on or to predict on, you will have to make sure that all the input the inputs are of equal length, and that's the reason for this padding, making shorter sentences as long as the longest sentences, so the inputs are of the same size, shape. So we should mimic our dataset like this example, which is, or if you look at the labels, it starts with an O, which means a non-entity token at the beginning. Then it's the B person, as John or Jan in my language. And then there's a location, Louvain, which is a city location. And then all the rest are non-entity tokens. So that's what our dataset has to look like, apart from all these padding tokens, which are handled by training the model. Now, since this tokenizer and model were trained on this kind of sentences, it is splitting it well and predicting it well. But let's say I want to add a few of my own custom samples, it goes horribly wrong. Firstly, it's not trained on my custom entity, so I would want this to be detected as a name, but that's not even in the dataset, so maybe person could come out, but it's not going to do what I would like to see. And then the second problem is this tokenization goes horribly wrong on unseen or unfamiliar sentences. And that makes it very hard for me to label the sentences correctly, because I cannot predict what the tokenizer is going to split on. I can predict these start of sentence and end of sentence tokens and mark them as an O, but everything in between I cannot predict. So special characters and it's splitting on parts of words and so on. We should fix that first. Even if we had labeled these sentences correctly, if the tokenizer splits it like that, it's not going to be correct, because the positioning of the labels will be misaligned with the actual tokens, let's say. That's not going to be good training data. So what we would want is more like this, where we get a sentence and it's nicely split on the name label and the actual name. Then it got start of sentence, end of sentence, and the rest are padding tokens. Then this is then a more correct label, non-entity, non-entity, which means the start of sentence, the name label, and then the actual name, which is the entity that I'm interested in, the custom entity label, specified above in my custom label set. I'm only using the I's, the B's, and the O's for the inner, outer, and begin labels, entity labels. And now that I'm here, let's talk about this attention mask. This is basically necessary to tell the model which are the tokens to pay attention to, which are these, and telling the model that it shouldn't pay attention to the padding tokens. That is what that's for, because all of these padding tokens will be also fed to the model, and that can cause problems instead of ignore it. So to accomplish the following tokenization, we'll have to train a tokenizer on our custom data set, which only contains the sentences, not the labels. There's also a good notebook to follow to do that. We're going to start from a pre-trained Roberta tokenizer. We need to use the fast one. You could use the transformers library, or you could start from a Robert tokenizer file. This trained corpus is basically just containing the sentences, which is to train our tokenizer on. I did also add some of the example sentences just to see if it's to make sure it still performs on this as well. And then after training, this is a nice output. Of course, I'm not showing my own dataset. I will show you that in the train notebook. Well, you've already seen it, that it performs well on that too. The confusion here was let's say I didn't include these samples, it would tokenize completely wrong on these kind of sentences, which is, yeah, it's okay because these are not in my data set, and I'm not going to be trying on these kind of sentences. But I had the expectation that because I'm starting from a pre-trained tokenizer, that it would still be able to perform on these without having to specifically add them into my own samples. So yeah, that's not the case. If you train a tokenizer on your own custom data, it's going to output all these files and only contain the vocabulary for your custom data set. But that's what we want to train on, so that is what we want. So now that I have that customly trained tokenizer, I can actually correctly label my data. So in my data prep, I can load it in C# by copying that custom tokenizer folder. We only need the vocab and the merges. But perhaps there's a way to just load the tokenizer JSON and have everything, because this contains both the vocabulary, which is basically the tokens and an assigned ID, token ID. But this also contains the merges and contains the configuration of special characters like start of sentence, padding token, even truncation and so on. So perhaps you can use a plain tokenizer and just load the tokenizer.json. I did not do that. I was just playing around with figuring out which tokenizer to use to mimic the tokenization like we did have in Python. So what I came up with was the BPE tokenizer with Roberta pre-tokenizer to assign those special characters like those G's before the split tokens. And here we can see our tokenizer performing as expected. And now we can easily assign labels to these sentences. Like this is going to be an O. This is going to be an O. This is going to be a B name entity label. And this is going to be another O. So then I basically use that tokenizer to, this is to create the initial training corpus, just containing the sentences. And then from those sentences, I applied the custom label entities. So bname, breed, ref ID, and so on to accomplish a correct label. So O for the start of sentence, O for the name label, bname for the name, and then O for the end of sentence. I'm not padding here. I couldn't find a way to pad using the tokenizer, but I just did it manually before inputting it into the model later on for predictions. Padding is not needed if you just want to do predictions on single inputs, so one sentence at a time. We'll see that later. So now we have a properly functioning tokenizer and a correctly labeled dataset to train our actual named entity recognition model on. So we can continue training on this data instead. So then I try to pad these labels and label IDs programmatically, but that's actually not necessary because the data collator or whatever during the training is going to take care of that. So I can actually remove this. Then I had a few mistakes. I tried to get these into the dataset as well, but I didn't label them correctly. So I'm just removing those non-entity rows. And then I'm training the pre-trained named entity recognition model on the Dutch one. I'm loading this one. Now basically copy it with my own configuration. So instead of their labels, I want to use my new labels, my ref ID, breed, age, name labels, which have a slightly different amount of labels. So I had to ignore mismatched sizes. And then label ID to label and label to ID are basically I didn't check if this is correct, but this is just adding the mapping from label to ID and ID to label. So for further usage, let's see in the exported to models, because otherwise you get these unclear label mapping. So it's better to specify these. I didn't do that before. And then training arguments. So it's all very similar, like the example notebooks from Hugging Face, slightly adapted. Batch size and number of train epochs, you can play around with that. I only did 3 epochs, but it did so only 3 training runs, but it performs pretty well. And that is this data collator that will dynamically pad the inputs received as well as the labels. So I didn't have to do that manually. And then label pad token, we pass the token ID of the padding token itself, which is ID 1 in our tokenizer index, let's say. Pass the new tokenizer. We do some, coming from the notebook, some ways how the evaluation would work, predictions versus actual, and then the recall, the F1, the precision, and so on. It's just an example. All these examples I added just to see what's the input, what's the output, and to adapt my own data and output to that. Which also I noticed they're only using the IOB scheme to label the entities, which is inside, outside, and beginning, something like that, instead of trying the below, which is unnecessarily more labels and could make it more difficult to predict on, since there's fewer lasts. There may be just more IH than last H, for example, and it might skew the predictions towards that. So it's not that useful. Computing the metrics, this -100, well, I'm not really using that. It basically wants to give like a very negative score to labels that are not interesting to the model, like those padding tokens, I would assume. But this is coming from a different example. Maybe this is for the CLS tokens or the whatever. So you can, but that's not applicable to this one, at least as far as I know. Then I'm simply splitting train tests because I want to test my model afterwards. Let's have a look at the test data, raskruising with breed, mixed breed, with the correct labels, label IDs, tokenized with the padding, the token IDs and the padding IDs, and then the attention mask telling the model which tokens to pay attention to. Okay. Although I already have the tokens and everything, tokenized stuff, I just did it again because I needed to have the input IDs in a tensor format and so on, and then simply add the labels in the manner that I need to provide it as a data dict. This is all explained in the links, and a train and a test data set. And instead of pandas series, it needed to be in the format of a dictionary. Simply checking that there's no other columns still in the data set before feeding it to the model. It gets the data collator, the train and test data set, the arguments, and then this is the model to train, which is that copied model containing the new labels and so on. Make sure you don't accidentally use the pre-trained model, because then the configuration is wrong if your labels are different than which should be the case. Pass the new tokenizer, not the old one, not the default one, and then they compute metrics, simply training for 3 epochs, 1, 2, 3, which seems like very high metrics, which could be overfit, could be, we'll see about that. performing well on the training and and on the test data, which is good. It's very simple. The data structure is very simple, of course, just very short sentences and all very similar. So the test and the training dataset will look very similar. So maybe that's the reason for the almost perfect model scores. Then we simply save the model and we can do some predictions again. Well, comparing the actual labels with the predicted labels. And then it still seems to output very high scores, 99.8. Simply checking out which sample, just doing single predictions now, to see what it predicts for this sentence. So H, that looks good. This I name should be wrong. There's no I name in here. But let's see. Looks like something's going wrong here because this is not the true label. Anyhow. But this is a symptom I noticed from the padding tokens. It's going to assign a 1, predict a 1 for a padding token, while it should actually be ignored, but the 1 index in the new labels, in my custom labels, is coincidentally I name. So this is actually one value that should be ignored. We'll see that in the C# code. Anyhow, we saved our model as Robert V2 Dutch NER, and then I added fine-tuned, and then we get the following output. These checkpoints are training checkpoints, but the output of the training is actually of the model should be in here. And then this folder, well, this is the model in PyTorch format or transformer format, let's say. This is not usable in the C#. We can't just use this in the C# code. We'll have to do an export to ONNX, which we did before for other models, and it's quite similar. So this time I'm loading this fine-tuned model coming from the saved model, which is the saved model. We're loading the model checkpoint, also the tokenizer from there. So the tokenizer is also saved alongside the model. If we evaluate, yeah, we see the model structure, the shapes and so on. And then the output shapes. Based on that, well, it's similar like the other one. These token ID type IDs are not necessary for this model. We basically need input IDs, attention mask, and then the output are the logits. We can simply export using Torch ONNX export. That ONNX model that I can now, so that's this one, Robert V2 Dutch NER fine-tuned.onnx. That's finally in a format that I can use in my C#. And let's see. And then that is exactly what I'm doing. So after the tokenizing, well, initializing the tokenizer based on our custom vocab and merges txt, using the Roberto pre-tokenizer to get those special characters as prefix, token prefixes, and the start of line and the end of line tokens. Some input sentences looking like my dataset, then some more looking like the dataset, but this is one blob, so I have not, this performs a bit worse because I don't have any dataset rows containing the entire thing. It does work well, but all these new lines are kind of tokenized differently, which I did not anticipate while training the tokenizer because it's not included in my dataset. And then this kind of text does not perform too well on. And then we still see that some of these things, the tokenizer gets it horribly wrong because Django is not exactly a value that's in the dataset that the tokenizer has seen. So that made me wonder do I have to retrain the tokenizer for every prediction that I want to make? That would be absurd. Luckily, that's not the case. Because we're now predicting, we're not. We don't have to label it correctly ourselves. We just input this to the model, and it should predict the labels, and it works pretty well, even though these things are split horribly. Just taking a look, we've got the start and the end, we've got the tokenization, we've got the token IDs with the end token and the start token. Yeah, there's multiple ways to do this. And go to tokens and go to IDs. Fortunately, I couldn't add padding that way, so I did that manually. If you do and go to tokens, it basically contains the value and the ID, so I'm just using that. And then we see the tokenization again. Here it's got the tokenization wrong, but well, it's not a big problem for the model. So because I made these years and months plural instead of singular, it's kind of tokenizing it awkwardly. And yeah, that added some tokens to the length. But still, you got the end and the start token, so that's fine. So this is the same but singular. So 2 year and 7 month in English, and that's tokenized differently. There's likely, of course, similar tokens in there, 330, 271, 267. There's just some added tokens in between. Then we've got sex female tokenized, then the name Django, which is not tokenized properly, but anyway. And then reference, and this is also not tokenized properly. Now we need to prepare the inputs because I want to predict on all these input sentences at once. I need to pad them to the same input length. For that, of course, first I need to know the max sequence, which is the longest one, contains the most tokens, and I'm gonna pad all the other inputs to that length, to the max sequence length. So what we need to pass, input IDs and attention mask. But for all the sentences, so for all the tokens, and I'm simply adding the pad IDs. Let's say there's 4, let's add 4 padding token IDs. And then in the attention mask, I'm basically telling the model, okay, if it's a padding token ID, put a 0 for the attention mask, and otherwise put a 1. So to not pay attention to the padding tokens. And you get the following. This is likely the longest one. So this is not padded. But then you see another one which is padded with all those 1s at the end and all the 0s that follow for the attention mask. Then these labels, yeah, that's our custom labels. We should likely load them from configuration from our that's sitting besides our model or something, instead of re-specifying them, just to make sure we don't wrongly position them. That would mess up the prediction. So we've got 5 input sentences this time. Each of those sentences with the input length of 13. So this becomes the shape for the input. We load our custom trained ONNX model, input IDs, input shape, creating these tensor values, and the same for the attention mask. This is simply, if you do one input at a time, the input shape can be of variable length, but if you want to do multiple inputs, multiple sentences, predict on multiple sentences at a time, you need to make sure the tokenized inputs are of equal length. Then we run the session, pass down input IDs and attention mask, run the session, so that's basically the predict function. And then we always get this output 0, and then that contains all the rest. I'm simply checking the shape of the output of the predictions to then the total count, so the amount of outputs that are in there. We should expect like a multidimensional array of 5 sentences containing at least 13 inputs, and then it seems to predict like 11 output values. And then that we should post-process accordingly. You can kind of also see that how they do. You can see how they do that in Python as well. But what the annoying part is here. So let's first take a look at the shape. So we've got a 5 for 5 sentences with 13 inputs, and then this 11 is kind of the prediction. These are like values between just values in long values that the model outputs, and then we need to apply what they call in Python an argmax. Is basically getting the index of the maximum value of the last axis, and that should contain that should be the label index of our custom labels. That's specific to a named entity recognition. If you're training an embedding model, the outputs are going to have to be post-processed differently. I think I briefly showed that in a previous video. What I wanted to say about this is pretty annoying. The only thing we can do with this output 0 is basically get the tensor data as span, and then that's unfortunately flattening our multidimensional array or shape of this shape. It's basically formatting it to a single dimension with 715 values. So now to do this argmax, to get this maximum value of to get the index of the maximum value of the last axis, we basically have to reconstruct this shape. So I simply did that by chunking the flattened output again, and then doing total count, so 715 divided by, what's the output count? You see, by 5, which should give me 143. What you could also do is do 13 times 11, which is also 143. Basically get the chunks that belong to the first sentence, for example, well, to each sentence. Get those data and post-process that accordingly. And then we get a pretty good result with one problem. We could likely solve it differently, but these attention mask tokens are included. Well, the padding tokens are included, and the model is predicting on that, unfortunately, and returning ones for the padding tokens, but the one in our custom label set corresponds to iname, which is not what we want. So I simply coded a way to drop those ones at the end, let's say, after the end of sentence. But there's likely a better way to do that with tensors and so on. Anyhow, the results are pretty good. Of course, I'm predicting on very similar data. You do see it's new data because the tokenizer hasn't seen it before, so it's splitting awkwardly, but it's basically age 2 years and 7 months, so it's that plural version, and it's getting as an O for non-entity, O for the label of the non-entity label, basically saying age, and then an O for the special character, and then it starts recognizing the age, which is all the following tokens, 2 years and 7 months. And then the final one is the end of line. So although the tokenizer didn't do it correctly, the prediction is accurate. Then you have the same value, but singular, non-plural, let's say. And it's also doing a good job predicting. And then sex, female, we've got the sex in there. So that's good. And to see that it's actually the predicted labels that I'm displaying, not the original ones. Then name Django, another awkward splitting, but it does get the name correct. So that's to say that despite the tokenizer doesn't handle it correctly, the model does predict it correctly. But then the reference ID, it got it wrong. It did tokenize incorrectly and predict incorrectly for those ending tokens. So the next steps for me would be to, of course, expand the data set with more complex examples or multi-line examples like this block, and then train on that as well. Well, label it correctly and train on that as well to do more advanced named entity recognition, more advanced extraction, text extraction. Okay, I'll end the video here. You can find the notebooks on kisco.com/members and or on my Patreon. Do check out my products, and if you want some free code, you can sign up for at the top to get the source code of my NuGet packages. Okay, so now I think I've showed you how to retrain advanced NLP models, BERT-based models, and I've already shown you about a year ago how to retrain computer vision models, or more like object detection, bounding box detection, and so on. What we haven't covered yet is training models ourselves using C# as only, or using Torch Sharp. That could be simple neural networks, could be convolutional neural networks, LSTMs, RNNs, recurring with time series data, could be autoencoders, could be segmentation models, could be even reinforcement learning. That may follow in the future, but it's now still uncertain. I just wanted to get you going with some basic machine learning concepts and how to apply it more practically as well.